Okay, welcome to Robotics 1. In today's class, we are going to talk about some important concepts. And first and foremost, let me talk about the transfer functions. So transfer functions, and we spent a lot of time on transfer function, is the ratio of output divided by input in Laplace domain. So you have output in Laplace and input in Laplace. Now, usually, if we have a robot or if we have any other system, so robot or any dynamical system, usually it is expressed as a transfer function. Now, when you talk about a transfer function, we kind of represent it as a block diagram. And we looked at this block diagram type of analysis when we try to solve transfer functions using Simulink. So this transfer function has some input, and this input gets multiplied by the transfer function, and that leads to output. So now this input to output relationship is scaled by the transfer function. And this transfer function could have uh, S as an independent variable. Now this is called as open loop. Why it's called as an open loop? Which means there is no direct relationship between the output and the input. Usually the open loop transfer function is represented as g of s. G of s is the transfer function that takes input and then that converts into an output. Now let's try to talk about the closed loop. So if you have a transfer function, I'm going to talk about it like g of s. Now what I'm going to do is I'm going to tap from the output and feed it to through a feedback, and the feedback transfer function is h of s. And then what I will do is I will sum it over here. So this is called as the summing junction. So I want to state what exactly is going on here. So say your output is y. Now the same output y is fed over here. Now what I'm going to say here is this is the input x. Now what happens here is you have x minus y that is fed into g of s. And once you do x minus y into g of s, that gives you the output, which is y. So just to note, this is the transfer function of feedback. This is called as plant. This is output, and this is input. Sometimes input is usually represented as u. So let me just write this as u. So this is u. So u is the input, y is the output, and we have this transfer function. So this is called as open loop, and this is called as the closed loop. Now, obviously, as you can see in open loop, the input has no clue where the output is. So for an example, you will supply the input and hope that output is what you desire. But in the case of closed loop, you are actually sampling the output, and then this output is compared with the input, and that comparison is fed to the plant. Now, this is super important because many a times what you want is you want to make sure that output is where the input wants it to be. Say, for an example, if you use a stepper motor, the stepper motor does not have any feedback. So it runs in an open loop. But if you use a servo motor, the servo motor would have an encoder and it will continuously track, it will continuously see what is the current value of output. And that output can be controlled by modulating the input. Now, what I want to do is the open loop transfer function. Now, let me write this down. Open loop transfer function, loop transfer function is g of s. Now, what I want to do is I want to find out closed loop transfer function. Now, what is the meaning of closed loop transfer function? A quick recap. If you look at the system, you have a summing junction, you have a plant transfer function g of s, you have a feedback transfer function h of s, and then you have an output. So you have u, this is plus, this is minus. What I want to do is I want to combine everything together. So, and this is very important. So I have u and I have y here. So what I want to do is I want to consider this as one block and find out the transfer function that includes plant, summing junction, and the feedback. So I want to find out a transfer function, something like this, wherein I have this block that is representing these three components. So this block comprises of summing junction and a plant transfer function and the feedback transfer function. So how do I do this? Actually, it's not difficult at all. So let's try to look at how the output is flowing. So we are tapping the output from Y. This output is being fed over here. The difference or the error, which is difference between the output E is equal to U minus Y. So the difference between the input and the output is fed to G of S. So I'm going to start with the first loop, something like this. So if you think about it, I have U minus Y. Actually, let me start from the beginning here. So check this out. So I have Y. Y is coming here. So Y would get multiplied with H of S, and I will have H of S times Y. H of S times Y would get fed over here, and I'm gonna have U on the left hand side. So when I start from the left hand side, I will have plus U minus H of S Y. The whole thing will get multiplied by G of S, and that is going to be Y. So I want you to look at what is happening here. Here, I'm feeding Y. this y gets multiplied with h of s. So on the left hand side of the feedback block, I have h of s times y. That's get fed into the summing junction. In the summing junction, you are getting u on the positive side and h of sy on the negative side, and that's get fed over here. This is error, and then multiplied by g of s is equal to y. So now what I'm going to do is I'm going to expand all this. So this becomes u times g of s minus h of s g of s y is equal to y. Now the transfer function is the relationship between the input, this is the input, and output. So transfer function is the relationship between the input and the output. So what I'm going to do is I'm going to combine some terms. So this is u gs is equal to 1 plus hs gs y, and then once again output divided by input is equal to g of s divided by 1 plus h of s g of s. Now this is a very important relationship. This is called as the closed loop transfer function. So this is called as the closed loop transfer function. Now I want you to understand the difference between the open loop transfer function g of s and the closed loop transfer function. What has happened because of the feedback is one thing, please observe here. Because of the feedback, due to feedback, the poles and zeros are modified. Which means the numerator and the denominator of the transfer function got changed. So, and this is what we want to analyze when we try to study the feedback system. So please remember this, whereas you have the open loop system and you have the closed loop system. Because of the open loop system, you don't have any feedback. It runs in the open loop. In the closed loop, you have a feedback transfer function. Now, some of you may ask me, what is feedback? Now, the feedback is simple encoder. And the encoder transfer function is something like a transfer function that converts angular measurement or angular velocity into some sort of digital output. So that is the transfer function. So now what we are going to do is we are going to use this again when we try to analyze different types of control systems. Now in last class, we talked about few important parameters and we did analyze in Matlab. So in today's lesson, let me define what we studied in last class. So in last class, we talked about something called as system analysis. So we had a system that had some properties, spring, mass, damping, and we actually came up with a mathematical model, and then we derived the transfer function, and then we looked at how does the system respond. Now, if you look at the plots that we generated time traces. So time trace, wherein you have time on x-axis and either the displacement on y-axis or the velocity on the y-axis. So this is called as the time response. So time response. So time response is the change in the state of the dynamical system, the change in the state of dynamical system in time when subjected to particular input. So time response. Now, there are two things in the time response. There could be a transient response. So transient response is the response that is changing, that is initially transient. So the response that depends upon the initial condition, the response that depends upon initial condition, and in the case of damped system, when the eigenvalues have negative real part, the transient response usually dies down. And then what you have is the steady state response. So you have steady state response. What happens with steady state response is that response continues to stay. So this response is due to some input. Due to input. Now, what's going to happen is there is time domain analysis, and then there is something called as the frequency domain analysis. So in the case of frequency domain analysis, we are interested in understanding how does the system behave with change in the frequency of the input. So for an example, what I want to tell you is understand this. So if you have a system, you can study the system behavior using the time response, or you can study the system behavior using the frequency response. A simple example is if you have a transfer function. So you have a transfer function, and this system is linear time invariant. And what you want to do is you want to feed this system with different inputs. If you consider the examples that we studied in last class, we had a simulating block, and then we added a step input. We supplied that with a ramp input, and we supplied that with a sinusoidal input. And then we studied the behavior of the system. So we observed that the system was something like this. So this is actually understanding in frequency response. So what we want to do is, here we want to extract two parameters. One is magnitude. Magnitude is how big or small the output is compared to input. And then the second one is phase. So whether the output is in phase or out of phase or is lagging. Now, to give you a very simple example, if you apply some input, is system going to respond quickly? That means the phase is minimal. In certain cases, you apply the input and you have to wait a long time till system starts uh, giving you some output. So that gives you a very high phase. And what we want to do is, for the linear time invariant system, by supplying certain types of input and observing the corresponding output, we can actually characterize the system completely. And this is an important observation. For linear time invariant system, for linear time invariant system, and a classic example is what we studied in last class, which is ms square plus cs plus k. For a linear time invariant system, by supplying different types of inputs, and when I say different types of inputs, you can actually change the frequency of the inputs too. So for an example, if you have a sinusoid, you can change the frequency of the sinusoid. You can observe, and observing output, we can characterize the system. Now, this is super important when we talk about something called as the Bode diagram. And the idea of a Bode diagram is, what you do is you supply the system with a sinusoidal input, but change the frequency. So I want you to focus on particularly on this. So in Bode diagram, I'm going to have a transfer function. I'm going to supply that transfer function with sinusoid, but its frequency changes. The frequency of the sinusoid changes. And then what I'm going to do is, I'm going to observe the magnitude, and then I'm going to observe the phase. And based on magnitude and phase, I should be able to uh, understand the system behavior completely. Now, one thing I want to talk about is the stability. Next thing is stability. The stability can be defined in terms of many parameters, or there are different definitions of stability. But as long as we are concerned, we will talk about bounded input, bounded output stability. So this is very simple, which means if you supply a system with a bounded input, the output does not blow up. So if you supply a bounded input, the system output is also bounded. So for an example, consider that you have a plant, and now I'm going to show plants as g of s, and there is an input, and say this input it's sinusoidal. So bounded input, bounded output means the system may amplify. Okay, the system may amplify, but still you're gonna have an upper bound and lower bound on the system output. So this is the bound on the input, and the output is also bounded. That means the system will not blow up in operation. And this is an important observation, and this usually happens when the eigenvalues or poles are on the left half plane. So this is the real axis, this is the imaginary axis, and if the eigenvalues are on the left hand side, you have bounded input, bounded output, stability. So this is where the eigenvalues or poles are. Now, what we are going to do is, in today's lesson, we are going to talk about uh, how to do this type of analysis using Matlab, and I will switch back and forth between the Matlab and the whiteboard. So now at this point, I'm gonna switch to Matlab. So you should be able to see my Matlab screen. And what I'm gonna do is, first and foremost, I'm going to construct a simple transfer function. And to construct, in the last lesson, I showed you how to perform the analysis using Simulink. In today's class, I will show you how to perform the same analysis using Matlab. So to create a transfer function, first you need to create an S variable. So this is the command. Type this in the Matlab. Then I want to create a transfer function. And this is the same transfer function as before, spring mass damper system. And what I'm going to do is, I'm going to first and foremost find the poles of the transfer function. And the command to find poles using Matlab is POLE, pole. Now I want you to run the command, highlight, and evaluate. Now, once this is done, you will see a transfer function. This is the same transfer function that you have here. And this tells me the poles of the system. So poles have negative real part. So the poles are -1 plus minus 2i. So these are the poles of the system. Now, a couple of classes before, we talked about converting the system into first order form. So we talked about converting the system into first order or state space form. So MATLAB can take a transfer function and convert that into a state space form, and the command for that is ss data. So the command is ss data. And what I want to do is I want to find out the eigenvalues of A. What I want to do is I want to find the eigenvalues of A. Now please note, once you run this code, you will find out that the poles that we got earlier are same as the eigenvalues. Now this little bit, this small example gives some useful insight. Now consider the term that is multiplying s square. This is nothing but the mass, value of mass. This term multiplying s is the value of damping, and this constant is the value of stiffness. And if you were to type A, please note this gives you a state space representation of the spring mass damper system. This is the state space representation of the spring mass damper system. So Matlab can convert from state space to transfer function, and it can come back and convert the transfer function into state space. Okay, any questions at this point? Now what I'm going to do is I am going to switch back to my screen. Okay, now next thing that I want to talk about is the concept of system order. And we talked about this in last lesson and lesson before that, but still I would like to write this down because this concept is important. The order of the dynamical system is nothing but the highest order of derivative. So for an example, if you have system x is equal to 5, this is called as zero order system. So or let me call it this as 4x is equal to 5. This is the zeroth order system. If you have 4x dot is equal to 5, this is the first order system. And if you have 4x double dot is equal to 5, this is the second order system. Now let's spend some time on understanding the first order system. So let's study first order systems in detail. So the first order system is usually given by this equation. y dot plus ay is equal to bu. Please note y is the output and u is the input. A and b are constants. This equation can also be written as something like tau y dot plus y is equal to kdc u. So in this particular case, what I do is I divide the equation by a. So tau is 1 by a. This equation is y dot plus y is equal to b by a u. And this is called as the standard form of the first order equation. This is called as the standard form of the first order equation. And many a times when you study the system, typically they will be written in the standard form. Now what I'm going to do is I'm going to take the Laplace transform. Once again, Laplace transform, I'm going to go from the variable t to s. Y of t gets written as y of s. Y dot of t gets written as s y of s. So this equation can be written as s y of s a y of s is equal to b, and u of t is written as capital U of s. So now I can write down the transfer function as output divided by input. So y of s divided by u of s. This equation can be written as b divided by s plus a. If you want to write the equation using the standard form, this equation can be written as k dc divided by tau s plus 1. So this is the equation that is written in the standard form. And one thing I just want to tell you, for first order system, tau and kdc completely characterize the system. So which means for a first order system, if you know value of tau, if you know value of kdc, that system is completely defined. So what are these two terms? So kdc is called as dc gain. So this is called as dc gain. So dc gain is nothing but the magnitude of the steady state step response to the magnitude of the step input. So I will write this definition down. DC gain is the ratio of magnitude of steady state step response to step input. Now, and it's also called as the value of the transfer function, the value of transfer function when s is equal to 0. So for an example, look at this transfer function, k dc divided by tau s plus 1. This is the transfer function. Now in this transfer function, substitute s is equal to 0. What you get here is nothing but k dc. So the value of the transfer function when s is equal to 0. Next term is important, and we talked about it. It's called as the time constant tau. Now, what is time constant? Time constant by definition is the amount of time the system takes to reach 63% of its final steady state response. Steady state response to step input. So please understand, in both the cases, for DC constant and time constant, our input is a step input. So we supply a step input and then we see how does the system behavior changes. Now, essentially, it gives you an insight on the time scales for system dynamics. Now, what I mean by that, I just want to give you a very simple example. Consider a spring. And what you do is you add some input, you add a weight. You will notice that the spring response is immediate. Now, what I want you to do is, I want you to visualize that you have a spring, and in addition to spring, that you have a damper. And then you apply the force, and you would see that depending upon the value of damping, the response is going to be more sluggish. So in other words, time constant, this is the first order system. And this is nothing but a zero order system. So you'll observe that because of the damper, the system is going to behave in a sluggish fashion. And that sluggishness is kind of tells you the system, how would the system behave when you are supplying some input. It could be a step input, or it could be a sinusoidal input, or any other input. The last thing is I want to talk about is the poles and zeros. Poles and zeros. Now you have a transfer function. This transfer function has a numerator, and this transfer function has a denominator. So the poles are values of s. Please note, s is the independent variable. For that value, denominator is 0. And zeros are values of s for which the numerator is equal to 0. Now, what you can see is, so when you have some zeros, the transfer function becomes 0. So at 0, transfer function becomes 0. At pole, transfer function becomes infinite, or denominator of the transfer function becomes 0. So if you look at the transfer function that we talked about, and this transfer function for the first order system, transfer function for the first order system is B divided by S plus A. It has no zeros, because there is no S in the numerator, and the poles, so S is equal to minus A is the pole. So this system has no zeros, but it has one pole. Now what I'm going to do is I'm going to go to Matlab and show you the analysis of the first order transfer function. Before I proceed, are there any questions at this point? If there are no questions, I will go ahead and share my Matlab screen. So now you should be able to see my Matlab script. Now, next thing is response of first order system. So what I'm going to do is I'm going to assume the DC gain of 5. I'm going to assume the DC gain of 5. I'm going to assume the time constant of 10. I'm going to assume the time constant of 10. And I'm going to assume input is equal to 1. I'm going to assume input is equal to 1. I will construct a first order transfer function. Now what I want you to do is I want you to kind of think about the analysis using the step input, and I'm going to apply a step input, and step input is given as u times g. Please note g is a transfer function, step input is u, and now I want you to run this system. So highlight and evaluate selection, and what's going to do is it should generate a step response, and I will show you how that step response looks. The step response looks something like this. Now I just want to make sure that everybody got the same step response. Okay. Now here is what I want you to do. I want you to right click on the step response. And once you right click on the step response, you should be able to see a prompt. Once you right click on the step response, you should be able to see a prompt, and there is something called as systems. Then the next is characteristics. Just hover over characteristic, and then you will see there is something called as the peak response, settling time, rise time, and then steady state. And as soon as you click them all, you will get these points in your step response. So you will see that in the step response, it will tell you the settling time is 39.1 second. It will tell you that the rise time is 22 seconds, and then it will show you that the steady state response or the final value is 5. And at this point, I just want you to quickly observe that our DC gain, okay, is 5. Our step input is 1. So the steady state response or the final value is 1 multiplied by the DC gain, which is 5. The final value is 5. Any question here? So now I'm going to switch back to my screen. So let me give you the formal definitions of settling time and rise time. So what do we mean by settling time? So settling time is the amount of time the system takes for the output to fall within certain percentage of steady state. It is the amount of time the system takes to fall within certain percentage of output. For, and again, what we are going to do is for step input, this is important, for step input. Now, you can actually think about it something like, let me give you a sort of a table, and depending upon what we are trying to analyze, there are different definitions. Say somebody may ask for 10% of settling time. Somebody may ask 5% of settling time. Somebody may ask maybe 2% of settling time. So if your settling time is 10%, TS is equal to 2.3 divided by A. If your settling time is 5%, then it is settling time TS is equal to 3 divided by A. If your settling time is 2%, then TS is equal to 3.9 divided by A. Now the next question is, what is rise time? Rise time is the amount of time the system needs so that the output goes to say 90% of the steady state output. So amount of time needed by the system to reach certain percent of steady steady state value. So for example, if we want 90% rise time, then what I'm gonna do is I'm gonna find out the time system takes to reach 90% of steady state value. Now, the last but important part in analysis is something called as the body plot. And this is very important. So the next is concept of body plot. And I will try to give you more physical interpretation of what the body plot is. Now, think about that you have a system which is I'm going to call is G of S, and now you are supplying this with sinusoids of different frequencies. So what you're going to do is you're going to supply this system with sinusoids of different frequencies. And clearly, the response of this system for these different frequencies is going to be different. So I'm going to have response, maybe it's something like this. Then maybe I will have the response for the second sinusoid, something like this. And I would observe that for at this frequency, a system kind of blows up, and that might be possible if the frequency equals the natural frequency. So what I'm going to do is from this input, this is the input, and from this output, I'm going to find out two things. I'm going to find out the magnitude ratio, and I'm going to find out phase. So I want to find out if I were to supply certain input, whether the output is greater than input, whether the output is same as input, or output is less than input. So that is the magnitude ratio. And next thing I want to look at is the phase, whether the input is along or in the same phase or input as output, or the output is lagging, or output maybe behaves completely differently. So if I want to understand this, the body plot actually comprises of two plots. It's also called as the body diagram. Body plot or diagram comprises of magnitude versus frequency, versus frequency, and phase versus frequency. Now, frequency is given in radians per second. Frequency is given in radians per second. And typically, the way we do it is we start from 0 and go all the way up to infinity. So think about it that you're starting from 0 and going all the way to infinity. It would be super duper difficult to draw this plot on the linear scale, because the linear scale means you will need an infinitely large, infinitely long paper. So usually it is plotted on the logarithmic scale. So this is done on log scale. So you can have very small values and very large values on the same plot. Same thing happens with the magnitude. The phase is given in degrees, and usually the phase is plotted on the linear scale, but magnitude is given in decibels. And decibel is nothing but the logarithmic representation of the magnitude. And so magnitude in dB is given as 20 log of 10 the magnitude. So whatever magnitude that you get from the analysis, you just convert that into a log scale. And why is this needed? Because we want to find out a very teeny tiny magnitude all the way to maybe infinite magnitude. And if we want to plot this on the graph, then we are gonna need a super duper big graph paper. So to show the magnitudes from very small value to very large value, to show frequencies from very small values to very large values, you can actually study the plot very nicely. Now what I'm going to do is I'm going to go to uh, Matlab, and then I will show you the how to do the body plot. So now you are on Matlab, and the transfer function that we are looking at is the transfer function of the first order system G, and the command for the body plot is nothing but body G, and this G has to be capital. And if you type this body G, you are gonna get the same plot as what I have over here. Now this gives you a body diagram, and as you can see that you have the frequency in the radians on the x-axis for the magnitude as well as phase. And you can notice that the magnitude is given in dB. And again, if you right click on this, it will tell you peak response, stability margin, and all other information. If you want to change the properties, you can change the scale, and rather than convert, so right click, and then the property editor will show up, and then you can change the scale. But here is what I want to show you, what this system is showing. This system shows me is as the frequency goes from 0 to a very high number, as the frequency goes from 0 to a very high number, I have initially about 14 dB of response. So basically about 14 dB of response. And then as the frequency goes on increasing, the system response becomes smaller, 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 and to the point that it goes to very, very small magnitude. So what this means is this system, as the frequency of the input sinusoid increases, the, the, the system is going to diminish the output. And you will notice that the bend is at the frequency that is equal to the absolute value of the pole. So please note our pole was at 1. So you can see this is the value at which the system started sloping down. And when the frequency was equal to the value of the pole, that is nothing but A, then the system response started going down. And this is like 20 dB, minus 20 dB per decade. It means for every 10 uh, frequency units, the slope is going down by minus 20 dB. If you look at the phase plot starts with 0, which means at low frequencies, the output is in the same phase as input. So it's about the same phase. But it becomes minus 90 degrees at very high frequency. At very high frequency, it becomes minus 90 degrees. So the Bode plot kind of tells you how does the system behave at low frequencies, how does the system behave at high frequencies. So looking at this Bode plot, I can see that at low frequencies, the amplitude, the output is going to be larger than the input. At low frequencies, the output is going to be larger than the input. But at high frequencies, the amplitude is going to be very, very small. So this system will sort of filter out the high frequency excitations. So that is what is the interpretation of this Bode plot. Any question before I proceed to the second order system? Now what I'm going to do is I'm going to talk about the similar analysis, but except now we are going to talk about the second order system. So for second order system, for second order system, highest derivative is 2. And the system, if you think about the examples, are spring mass damper system, and the equation of motion is typically given as my double dot plus b dot plus ky is equal to f of t, where m is the mass, b is the damping coefficient, and k is the stiffness. Damping, the stiffness, and this is input. This equation can also be written as y double dot plus 2 zeta omega n y dot plus omega n square y is equal to kdc omega n square u. Now please note, zeta is called as damping coefficient. And this damping coefficient is given as B divided by 2 under root mk. So this is second term in y dot. It's omega n. The next thing is omega n is called as natural frequency. This is given as square root of k by m. And one thing I want you to understand that B, K, and M, they come from the system parameters. So M is mass, K is stiffness, and B is the damping coefficient. Now, if you were to find out the transfer function of the second order system, and we derived this in last class, it's something as 1 divided by ms square plus bs plus k. And alternatively, this can be written as k dc omega n square divided by s square plus 2 zeta omega n plus omega n square. Now here I just want to tell you k dc is nothing but the dc gain for the second order system. And dc gain is, if you think about it, dc gain is the value of transfer function when s is equal to 0. So when s is equal to 0, the transfer function gives you dc gain. So what I'm going to do is I'm going to write down this m s square plus bs plus k, and this s becomes 0, this becomes 0. So dc gain is 1 divided by k. The damping ratio is nothing but defined as, I gave you the definition of damping ratio, and this is the definition of damping ratio. This is the ratio between the system's damping coefficient. So damping coefficient, so this is also called a damping ratio. So this is damping coefficient ratio, which means you take a damping coefficient and divide that by square root, 2 square root mk. Now for this system, again, it is possible to find out pole and zeros. And to find pole and zeros, as we know, the numerator, you'll equate it to 0. That will get you zeros. And denominator, you equate it to 0, and that gives you poles. So now I'm going to go to Matlab, and in 1 minute, I will show you how this system can be analyzed. So for second order system, what I want you to run this code. And this is exactly similar as the first order system. So highlight and run. And then you will see something called as the PZ map that will show you what is the value of pole. Then if you want to do the step input, just add this additional term, this additional command, and then it will show you the step input of the system. So you will see the step input the way I have shown here. You can right click, and again, you can do the peak time, settling time, rise time, and then you can find out the steady state. So what we can do is we can actually look at the system, and then using Matlab, we can analyze. I'm going to stop here, but I would be happy to answer any questions that you may have.